In the summer of 1997, a heavy, low-frequency sound surged through the Pacific Ocean. Its acoustic footprint was so immense that it implied a source significantly larger than a blue whale. The signal carried enough energy to trigger underwater recording stations positioned over 3,200 kilometers apart simultaneously. The researchers who first cataloged this data were from NOAA, utilizing a vast underwater surveillance network recently made available by the United States Navy. This network, the SOSUS array, was a product of the Cold War. The Navy had installed thousands of microphones across the seafloor for the specific purpose of tracking the engine signatures of Soviet nuclear submarines. When scientists began using this military infrastructure to listen to the natural world, they found that the array was picking up violent, high-energy anomalies that the technology was never intended to analyze. To understand how a single sound can be heard across an entire ocean basin, we have to look at a layer of the deep known as the SOFAR channel. This diagram shows a unique depth, usually between 700 and 1,000 meters, where water temperature and pressure create a natural waveguide. Sound waves entering this layer become trapped, refracting between the boundaries above and below, allowing them to travel for thousands of miles without losing their intensity. Starting in 1990, NOAA scientists used this channel to monitor the ocean, expecting to map the predictable sounds of whale migrations and undersea earthquakes. Instead, the array captured a series of massive, repetitive events, given names like train and slow down. These sounds resembled heavy materials being dragged across the ocean floor, lasting for minutes at a time. The SOFAR channel revealed that the deep ocean was far more active than surface observations suggested, filled with energetic events that remained invisible to our satellites. The Bloop became a global mystery because it sounded like a biological entity, but that audio was actually sped up 16 times before it was released to the public. This created a psychoacoustic trap. The human brain is highly efficient at finding biological patterns, and when that low-frequency grind was compressed, our ears interpreted the rhythm as a giant animal breathing. Determining the actual source required closer data. Scientists eventually deployed microphones directly along the coast of Antarctica to capture these signals at their point of origin. By 2008, forensics confirmed that the Bloop was an icequake. When massive glaciers fracture and scrape against the seafloor, they generate low-frequency vibrations powerful enough to travel across entire ocean basins. While acoustic tracking successfully identified the icequakes, the same technical limitations of this hardware are why other sounds remain unidentified mysteries today. The most fundamental rule of identifying an undersea sound is triangulation. To pinpoint an origin, a sound must be recorded by at least 3 geographically separate microphones. This allows computers to calculate the time delays and draw intersecting lines back to a single coordinate. This rule is why a 1997 anomaly called the whistle, a clean musical note recorded in the deep, remains unsolved. It was only detected by a single microphone on the array. Without 2 other data points, the intersecting lines couldn't be drawn. Without that third point of data, the tracking system is mathematically paralyzed. We can hear the sound, but it is impossible to know its location or its source. Then there is the upsweep, a rhythmic, alarm-like sound first detected in 1991 that is still occurring today, 34 years later. Unlike the whistle, the upsweep was loud enough to be captured by multiple stations, giving scientists its exact location. Those coordinates point to a remote area of the South Pacific, far from any coastline. The problem is, bathymetric maps show this region as a featureless void. There are no known islands, volcanic ridges, or documented shipwrecks at those coordinates. Most strangely, the intensity of the upsweep fluctuates with the seasons. It grows stronger and weaker throughout the year, suggesting a source that is dynamic rather than a static geological feature. The upsweep demonstrates that we can have the technology to know exactly where a sound is coming from while still remaining entirely blind to what is making it. There is a disconnect between our ability to track metal submarines and our ability to see the ocean floor. We have high-resolution acoustic data, but very little visual confirmation of the deep seabed. This forces scientists to make educated guesses. They often attribute strange acoustics to unmapped volcanic activity, since they lack camera arrays to monitor the seafloor. Over 95% of the ocean remains unexplored, and more than 80% of its species are estimated to be undiscovered. The SOSS array was built for a very specific human purpose: to listen for machinery. It was never intended to be a comprehensive tool for exploring a complex, living ecosystem. Consider how many high-energy acoustic events are occurring right now, completely undetected, simply because they don't happen to pass by a scattered network of Cold War microphones. As long as our primary way of listening to the deep is through repurposed military hardware, the bottom of the ocean will remain a realm of extreme conditions and unsolved secrets.